Welcome to the HardFiber webinar. In this webinar, we will discuss the following items: business considerations, system architecture, system components, scalability, and we'll show a video on how easy it is to upgrade a UR relay that was using hardwired connections to one with a process bus and brick configuration. Next, we'll look at the trends and expectations for protection and control. From cost pressure trends, we're looking for a reduction in total installed cost. Available workforce, the expectation here is less labor and relaxed skill set requirements. The focus on key competencies, we're looking for a transfer of work. New external environment, we're looking for a simple solution with minimum deployment time. So here's some ways to optimize our resources. We've got two categories here. We have our total installed cost of protection and control, consisting of materials, labor, and intangibles. You can see a list there of materials being PNC devices, terminal blocks, control cables, hookup wires, test isolation switches. Labor being engineering for design and drafting, construction, commissioning, maintenance, and training. And intangibles, the control buildings, document management, stranded labor and handoffs, and workforce skill set requirements. So areas where we can actually optimize in is in the engineering labor, drafting handoffs, construction effort, construction skill sets, worker safety, commissioning effort, maintenance effort, and inadvertent tripping. So the optimized labor pipeline leads to cost savings. Here we have a cost analysis for a project with a budget of $407,000. Using a hardwired approach, the majority of the costs are with labor, consuming 73% of the budget, while 27% of the budget is consumed by materials. In a system utilizing a process bus system, there's a shift in the way the budget is divided. 42% of the budget is consumed by materials, while labor consumes 34% of the remaining budget, leaving the project with a 25% savings. Process bus is a term used to describe a protection and control system that uses a digital communications architecture to carry information between the switchyard and protection and control devices in the control building. This information consists of sample values, equipment status, and output commands. IEC 61850 is the international standard that defines the specific communication protocol for process bus implementation used for protection and control applications. In other words, it's a technical way of providing a mission-critical function for protection and control systems. 61850, its goal is to design out all copper signaling between the switchgear and the switchyard. The other thing that this protocol does is it tries to find achievable ways, cost-saving methods, by simplifying engineering, drafting, construction, commissioning, and ownership. Bricks are the process bus merging units that are installed in the switchyard to provide complete I/O capability for the system, data acquisition, and outputs. The brick converts copper signals to and from digital optical signals. The copper signals include things such as CTs, VTs, contact inputs, and contact outputs. There is no processing done in the brick. All calculations and programming are performed in the UR and not the brick. For mission-critical signals, we can also install redundant bricks. Bricks are connected via multi-fiber cables. The outdoor fiber cables can be placed in cable trenches or directly buried. The outdoor fiber cables have a dual function. They not only provide communication between the switchyard and the control house, but it also supplies power to the brick via copper wires integrated in the fiber cables. The cable lengths are predefined, and the ends of the cable are terminated at the factory, with one in a circular ring connector and the other end being a single high-density cable connector. The copper connections that would normally be placed in the cable trenches to provide protection, control, and monitoring between the switchyard and control house are eliminated. The connections going to circuit breakers, CTs, PTs, disconnects, ground switches, sensors, are interfaced to the brick in the switchyard, therefore reducing the amounts of copper cable requirements between the switchyard and the control house. One end of the outdoor fiber cable terminates at the brick. The other end terminates into the fiber cross-connect panel. The cross-connect panels are where individual fibers in the outdoor cables are patch corded to individual fibers of indoor cables, completing the association between the relays and the brick. The cross-connect panel also distributes DC power to the bricks via the outdoor fiber cables. From the cross-connect panel, the indoor fiber cables complete the optical connection between the process bus module ports of the relays and the brick in the switchyard. The process bus module converts the brick's digital optical signals for use in the UR series devices. Here is an overview of a system utilizing the HardFiber configuration. The primary role of bricks is to limit the amount of copper wiring by containing it as close to the power apparatus as possible and to provide a transparent and unified digital interface to the relays. Conceptually, bricks should be thought of as a simple signal converter rather than full-featured IEDs. No additional items such as Ethernet switches, clocks, or clock distribution systems are needed. Each brick has the ability to communicate with up to 4 UR relays. Each UR has the ability to communicate with up to 8 brick merging units. Let's recap the process bus system. The copper cables make the connections between the copper terminals inside the power equipment to the bricks mounted in the switchyard, typically on the outside of the equipment. The bricks convert copper signals to a digital optical signal. The outdoor fiber cable makes the optical connection between the bricks in the switchyard and the cross-connect panels in the control house. The cross-connect panels are where individual fibers and the outdoor cables are patch corded to individual fibers of indoor cables, completing the association between the relays and the bricks. The indoor fiber cables make the optical connection between the cross-connect panel and the process bus ports of the relays, reducing dozens of copper wires at the relay. The process card, in turn, converts brick digital signals for the UR. Here's an example of a traditional switchyard construction. At 1, we have traditional breaker wiring of CTs, VTs, I/O, and control. At 2, we have large amounts of copper cables that are laid out in a cable trench that require terminations at both ends. 3, thousands of copper wires from the switchyard routed to the control house. And 4, labor-intensive power wire installation required at the relay panel. Our solution for eliminating complexity: 1. From the traditional breaker wiring to the brick merging unit. This eliminates 33% of the breaker terminations. 2. Traditional cable trench. 40% less cabling required because both ends of the outdoor cable are terminated. 3. Instead of terminating thousands of individual copper wires from a switchyard, the outdoor cable connects to the cross-connect panel, eliminating 90% of control building terminations. 4. Labor-intensive copper wiring on relay panels are replaced with a few fiber optic connections. The HardFiber system uses IEC 61850 to communicate measurements and commands between bricks and relays in the control building over dedicated point-to-point fiber optic connections that avoid cybersecurity issues altogether. The communication from the brick uses IEC 61850-9-2 as sampled measured values to publish. The brick uses a goose message to sample the measured values. Communication to the brick is done as per IEC 61850-8-1 as a goose subscription. The brick HardFiber is IEC 61850 certified as per KEMA. The brick communicates according to the IEC 61850 International Standard Communications Network and Systems and Substation First Edition. The brick is communicated to via IEC 61850-8-1, and communication is received from the brick via IEC 61850-9. The brick is shown to be interoperable as specified in the Protocol Implementation Conformance Statement, known as PICS, Model Implementation Conformance Statement, known as MICS, Protocol Implementation Extra Information for Testing, known as PICSIT, and IED Configuration Description, known as ICD specifications. If you're interested in getting a copy of the KEMA test summary, please go to www.gegridsolutions.com. Bricks are the input-output interface to the copper world. Their function is to acquire the AC current and voltage waveforms and contact input status from a primary power system element and transmit this information to the control house via optical fiber. Measurements are transmitted through 4 channels of communications to 4 separate IEDs. The 4 IEDs have the ability to control inputs and outputs through a shared I/O feature. Keeping true to the existing topology of traditional substations, each protection and control device included in the zone of protection will be connected directly to the bricks through dedicated fiber optic connections. The brick is a rugged device designed for mounting on or inside the power supply elements in the switchyard. It has a rating of IP66, which means dust tight and protected against heavy seas or powerful jets of water. There are no fans or vents in the chassis of the brick. All interfaces have connectors. There are 4 different configurations available. CC55, which consists of 8 5-amp CTs, CV50, which consists of 4 VT connections and 4 5-amp CTs. CC11 is 8 1-amp CTs. CV10 has 4 VT and 4 1-amp CTs. The brick power supply range is 88 to 300 volts DC. Each brick has 3 transducers, 18 contact inputs, 4 solid-state relay contact outputs, 1 latching contact, 2 Form C contacts. Each brick represents a DSP module within the UR relay. There are 4 connectors on a brick labeled A, B, C, and D. Each connector has a specific cable with the matching markings of A, B, C, and D that mate with it. Those cables have mil-spec DTL 38999 connectors on the brick side that have a long history of reliable operation in harsh environment. The cable connectors are key to prevent incorrect mating. The rings on the outside of the connector are used to fasten the cable to the brick. The ring is turned until the red band on the connector is covered. The easiest way to install the cables is to place the brick on a flat surface and have the marking on the cable facing up. The other ends of the copper cables, B, C, and D, have pigtailed ends that are intended for short runs between the brick and the apparatus. They can be cut to size and have the conductor number printed on each. The first cable we'll look at is the FOA cable. This fiber optic cable connects to connector A. The FOA cables are used to connect the brick to the cross-connect panel. The cable contains 4 multi-mode 50/125 micrometer optical cables, 1 for each brick's digital core, and 2 16-gauge copper conductors for supplying electrical power to the brick. The FOA cable is terminated in an orange plastic housing that contains and organizes a quad LC optical fiber coupler, an electrical power connector, and an outdoor fiber cable, 2 power fuses. The fuses provide protection for short circuits on both the cable and the brick and have a high interrupting rating suitable for use on most station battery distribution systems. The shell snaps into the rear of the cross-connect panel and is secured with 2 captive screws. Installed, the electrical connector mates with the power and ground connections from the distribution bus in the cross-connect panel. The optical fiber coupler projects through an opening to the front of the panel, allowing LC patch cords to directly couple with the cable fiber, limiting the number of connections and thus signal losses and potential trouble spots. The FOA cable ends are predetermined at the factory. The cable can be ordered from a length of 1 meter up to 500 meters in increments of 1 meter. As an alternate, there is a GE supplied outdoor fiber splice cable. The outdoor fiber splice cable consists of a circular plug connector similar to the outdoor end of the outdoor fiber cable with pre-assembled separate fiber and copper cables at the other end. The cable is available in 1 length only, which is 5 meters in length. This relieves the need to terminate fibers in a circular connector and provides an environmentally secure connector back shell. The fiber cable can be routed into a marshalling box and there spliced to generic fiber cables that bring the brick's optical signals to the relays in the control house. The copper cable can be routed to a DC distribution box to supply brick power. Short circuit protection, for example things such as fusings, needs to be provided for the brick power input. Connector B is the location of the contact outputs within the brick. Each brick contains 4 solid-state relay contact outputs. Each SSR contact output is designed to interface directly to a breaker, switch, strip, or closed circuit, or to DC-powered conventional protection and control equipment. These output features very short operating times and are capable of interrupting large, highly inductive DC currents. Solid-state relays are polarity sensitive and have both voltage and current monitoring. Each brick provides 2 Form C contact outputs. Each Form C contact output is designed for general purpose applications in either AC or DC circuits such as a tap changer, a raised lower control, and cooling, fan, pump control. The switching element inside the brick is an electromechanical relay with a single Form C contact. Each brick provides a single latching output. The latching outputs are designed for applications where the contact state must not change except by explicit commands, such as in a lockout application. The switching element inside the brick is a bi-stable magnetically latched electromechanical relay with a single contact brought out. This contact is suitable in either AC or DC circuits. The copper cable that connects to connector B is the CUB. It is available in specific lengths of 2, 5, 10, or 20 meter lengths. Connector C is the location of the contact inputs within the brick. The contact inputs are designed to interface to dedicated, isolated, dry contacts or their electronic equivalents. Examples include breaker disconnect position switches, temperature switches, pressure switches, and flow switches. In addition to mechanical contacts, brick contact inputs can be driven by solid-state relays, such as the brick solid-state relay output contacts. All contact inputs of a given brick use a common return. Since the bricks use a dry contact input, connecting a brick contact input to an external power supply can cause permanent damage to the brick. The brick does not implement a debounce delay on contact inputs. The contact inputs are sampled at the same rate as the AC inputs. If contact debounce delays are needed, it may be implemented in the UR relay as required. The DC inputs can be used with any of the following devices: RTDs, and we have a choice of 3, 100 ohm RTD, 100 ohm nickel, 120 ohm nickel, 100 ohm platinum. Potentiometers, such as a transformer tap position and a DC loop transducer, where we can retrieve 4 to 20 milliamp readings. The cable lengths are available in 2 meters, 5 meter, 10 meter, or 20 meter lengths. Connector D is the interface to the CTs and VTs. The copper cable CUD are the AC input cables and are keyed so that they only mate with bricks of the corresponding type, so the current circuit is not mistakenly connected to a voltage input or vice versa. The brick doesn't have any internal shorting bars on the CT circuits, so when disconnecting an AC input cables that carry current transformer circuits from connector D, care must be taken to avoid open circuiting an energized current transformer secondary. A shorting device at the field termination end of the cable is advised to short the current transformer circuits prior to disconnecting the cable. To bring attention to this restriction, a yellow metal ring is installed that completely covers the connector ring and is secured with a padlock, seal, or tag. This security mechanism provides an important physical and procedural safety barrier for work protection practices to prevent unintentional opening of the live CT secondary circuits. The CUD cable is available in 2, 5, 10, and 20 meter lengths. There are 5 LEDs on the front of the brick, 1 for the analog core, and the 4 represent each one of the digital cores, which summarize the state of the brick. The LEDs report self-monitoring functions that detect virtually any internal problem, as well as problems with the received optical signals. Each digital core also reports the details of its own internal diagnostic alarms, as well as common alarms related to the analog core back to the corresponding relay. Measurements are also sent to the relay indicating the optical signal sent and received signals levels, as well as the internal temperature of the brick. In general, the color of the indicator LEDs indicates the state of the brick. A green color indicates that there are no errors, while a red color indicates an error is detected. The table provides the conditions for the analog core and digital core indicators. Here are some examples of the brick being subjected to vigorous environment testing, such as dust ingress, water ingress, and sun loading. The operating temperature of the brick is minus 40 degrees Celsius to 70 degrees Celsius. Humidity non-condensing is 100% at 40 degrees Celsius and can be used in altitude up to 2,000 meters. Each cross-connect panel contains 16 receptacles for up to 16 outdoor or indoor fiber cables in any combination. The cable plugs snap into the receptacles at the rear and are secured with 2 captive screws. The plug's optical fiber couplers project through the front, where standard LC multimode 5125 micrometer patch cords can be directly connected to cable fibers to form the necessary cross connections. The copper connector pins of outdoor cable plugs mate with sockets in a receptacle that bust them to a common power input terminal block that also at the rear and to chassis ground. Where an indoor cable is present, the corresponding power socket is unused. Cross-connect panels are designed for 19-inch rack mounting. They are 4U high, which is 7 inches or 178 millimeters, and may be stacked vertically to increase capacity. A transparent door that normally covers the patch cord compartment swings down for easy access. Cutouts on the top and the bottom of each side allow patch cords to be routed between stacked panels. Here we are looking at the inside of the cross-connect panel. The receptacles in each cross-connect panel are labeled 1 through 16, both on the front and on the rear. Additional labeling on the front designates the fibers 1 through 4 in each cable. These fiber numbers correspond to the brick core numbers where an outdoor cable is present. Where an indoor cable is present, the numbers at the receptacle match the fiber cables that are attached to the process card. The fiber cables are labeled as 1 to 4, where 1 is blue, 2 is orange, 3 is green, and 4 is brown. Any one of these fiber cables can be connected to any one of the ports on the process module. Cross-connect panels also serve as DC power distribution panels for the bricks. For troubleshooting purposes, several LED indicators are visible through the transparent cross-connect panel door. A red LED indicates the presence of power with the correct polarity. Green LEDs, one located next to each cable receptacle, indicates that there is a brick drawing power through that receptacle. If there is no cable or an indoor cable installed in a particular receptacle, the green LED will not illuminate. This LED will extinguish if the brick in that position is disconnected or a fuse blows. The process card module is an optional module that slides into a standard UR, making it compliant with the Process Bus protocol and providing it access to the connected bricks. Each module is capable of communicating with up to 8 bricks. UR series devices with a process card use AC signal sources in the same ways to conventional UR series relays. For a protection reference, the UR can be programmed using up to 6 sources. No new software or software modification is required. The process bus operates with other conventional I/O and inter-relay communication modules. However, there is a conflict between the process bus module and the DSP and transducer modules. The process bus module slides into the H slot of the UR chassis like other modules. In place of the typical terminal block module mounted at the rear of the UR, there is a black metal cover with a slot for the optical fiber port connectors of the process card to project through. The black metal cover is labeled to identify the port designations and their diagnostic LED indicators. To avoid fiber damage through the fibers being inadvertently left connected while the process card is withdrawn from the front, 2 screws secure the process card from the rear. These screws must be removed from the rear and the fiber disconnected before the process card is removed. The 8 optical fiber ports are the only user connections to the module. There are no copper connections. The module is available in these configurations: 81A, 81B, 81H, and 81V. The FOR cable, the indoor fiber cable, are used to connect the process card in the relays to the cross-connect panel. The cables contain 4 multi-mode 50 125 micrometer optical fibers. This cable contains no electrical conductive components. One end is terminated with the orange connector and the other end is terminated with fiber optic LC type connectors. Each one of the fibers are color coded as blue, orange, green, and brown and labeled with a number to match the fiber connection on the cross-connect panel receptacle. It is available in varying lengths from 30 to 50 meters long. The brick acts as multiple merging units in one device. The analog core interfaces with the copper input and output signals of the primary equipment, providing proper isolation against noise and other interference, converts analog signals to digital signals, and presents copies of these signals independently to each of the 4 digital cores using 4 independent digital data links. The analog core also operates its contact outputs in response to commands received from the digital cores via these 4 links. Each digital core transmits the data acquired from the analog core to the control house via an optical fiber Ethernet link. In the control house, each digital core can be cross-connected to a different relay, or a single brick can operate with up to 4 relays. Each digital core is completely independent of the other digital cores in order that each of the relays connected to the brick be independent of the others. Thus, each relay can sample at a different rate, can run different firmware versions, can even be from a different manufacturer with different process bus implementations. The power supply conditions the DC power received from a cross-connect panel via copper connectors embedded in the outdoor fiber cables and distributes power at the appropriate internal voltages to the analog and digital cores. The DC power is expected to originate from a 125 or a 250 volt DC station battery source. The brick can operate between 80 to 300 volts DC. Here's an example of connecting two bricks with two URs through the cross-connect panel. Using the cross-connect patch cables, core 1 of brick 1 is connected to IED 1 port 1, and core 2 of brick 2 is connected to IED 1 port 2. Core 3 of brick 1 is connected to IED 2 port 1, and core 3 of brick 2 is connected to IED 2 port 2. You can see that the use of the cross-connect panel allows for easy expansion for the addition of more bricks and IEDs. Typical applications for the brick are the retrofit and greenfield installations for power generation, transmission and distribution systems, generator, transformer, transmission line, bus, feeder, motor, capacitor bank, wide area network protection, distributed bay control, digital fault and sequence event recording, substation automation, and air insulated and gas insulated substations. This video will show you how to upgrade an existing hardwired UR relay to the UR using the brick. So the things that we're going to do is we're going to remove the card from slot F. We're going to move the module from slot H. We're going to insert the process module into slot H, the H81 card, and then I'll show you how to update the order code so that it reflects the new configuration. So one of the first things we're going to do is, let me show you the hardware that we're going to be working with. So here's the UR relay and the H81 card. This one here. We have our cross-connect panel on the bottom, and we have our brick that'll be on top there. So the first thing that we need to do is we need to power down the relay. With the relay powered down, we're going to go ahead and we're going to remove the F card and the H card. Now the reason we're removing these other cards is because the brick takes the place of the DSP card. So what we're going to do here is we're going to remove the card in F slot. Let's put it off to the side. And we'll take out the H81 card. From the back, we're going to need to remove the terminal strip off the back. With the relay spun around, we're going to take a look at the back. So we're going to remove the terminal strip off the back. There are 6 screws that are holding this in place. 3 on the bottom and 3 on the top. So I've taken out the bottom 3 screws, and I'm going to work on the top 3. This now will allow us to remove the module. Sorry, the terminal block. And now I'm going to spin the relay around again. And now we're going to take the H81 card and insert it. And it goes into slot H. Open up the tabs, push it straight back, and it goes. So we'll plug the display cable back in, close the door, and we'll power up. So one of the first things we'll see when we first power this up is we'll see a message like this. This says equipment mismatch, because we did take out the F slot card and we've inserted the new H card, and it gives us this kind of a message, the equipment mismatch. So what we need to do is we have to go through the procedure to do an update order code. So the next thing we're going to do is we're going to update the order code on the relay. It's done from the front panel. You press the menu button till you get the commands, And then on the relay maintenance, you're going to press the message write button, which will bring you into this column here, which starts off with the perform lamp test. You're going to press the message down, get to update order code, and then from update order code, you're going to use the value keys on the front panel to change the no to a yes. You'll press enter, and then the relay will go through a reboot sequence. So the relay will shut down, and as it's rebooting, it's going to update its internal order code. So let's go ahead and do this. From the front of the relay, we'll press the menu button until we get to commands. First thing we'll see is relay maintenance. We're going to go to the right. The first thing we see is update perform lamp test. No, we're going to go message down. Update order code. Use the value key to change it from no to yes. And press enter. The relay will now go through the reboot sequence. It's going to evaluate everything that's in the chassis and update its internal order code. Now, one thing to keep in mind, when this occurs, you're going to lose all the settings in the relay. Now that the relay is updated, now that it's rebooted, we're going to go back to the software and update the order code in the InterVista program. So now the next thing we'll do is we'll just go in and we'll update the order code. We can do that by device setup. Let's maintain what we have, and we'll come in here. We'll select our individual connections. I'll go with the Ethernet one, and select read order code. This will now go out to the relay, and it'll update the program to show the new order code and the version number. We select OK. This will now update this information over here. So there's our new order code. So next thing we'll look at is the HardFiber hardware. So this is the configuration that we're going to be using. There's the cable that we plugged in the back. This is plugged into slot number 16, and this is the cable that's going from the brick to the cross connect panel. And position number 8, we've got the other cable that's going between the cross connect panel and the UR relay. These are the jumpers that I put in. So once again, because this one's connected to the brick, this is core 1, core 2, core 3, core 4. And with the jumpers that I put in straight across, core number 4 is in position 1, 3 is in position 2, core number 2 is in position 3, and core number 1 is in position 4. These positions, these are all connected, they all have their unique connections. These are known as P1, P2, P3, P4. So in the video, what I've done is connected the individual cables into P1 going into 1B, P2 going into 2B, P3 going into 3B, and P4 going into 4B. Now this is important because we're going to need this for the programming. The next thing we'll focus on is the cross connect box. So pressing down the door, we have 16 positions to work with. This cable, this is the FOA cable, has 2 screws in the end. There's one on top and one on the bottom that gets fastened to the back of the box. So I've spun the box around. The cable simply plugs in this manner. There are 2 screws that need to be tightened down. So this is the where it gets fastened down. Now this is the FOA cable with the fiber optic connection on it. Now we're going to connect the other cable that goes between the cross connect box and the universal relay. So the FOR cable, which goes between the cross connect and the relay, looks like this. It has that same head, and it has 4 channels of fiber optic cables. Now we'll pick any position in there as well. It's the same concept. Now I'll turn the box around. This is our 2 connections. This one's going between the brick and the cross connect panel. The bottom one is going to the universal relay. The other end of this cable will be going into the brick to power it up. This is where the box is powered up. We've got the connecting screwed in all the way, and we've got a green light indicating that the device is operational. The other cable, this is the FOR cable. This is the one from the cross connect panel that plugs into the 8 individual channels on the back of the H81 card. So I'll just place one in every channel. So I put P1 in the top one, P2 in the second, P3 in the third, and P4 in the fourth. Now typically these would be the different connections for from 4 different brick modules. We're just going to plug in all 4 just to show you how to configure it in the software. Now the connections are made in this way. We've got 4 channels coming out of the brick, and we've got 4 channels coming into the relay. Now we've got these cables that come standard with the device, and what we're going to do is we're going to take each one and just, like a patch cord, just connect one into each one. You can see all 4 channels have lit up on the box. So all 4 channels have lit up on the box. They're red, indicating that the communication hasn't been established correctly between the brick and the UR relay. Just a quick comment. The bottom one, not the bottom connection here that's lit up here, this is the actual indicator that this is a brick connection, and we can see the 4 different channels here. Channel 1, channel 2, channel 3, channel 4. They're labeled more as core 1, core 2, core 3, core 4. So this core 1 is the 1 LED indicator, core 2 is for number 2, so forth, so on. If I remove one of the cables, you can see, so I took out channel core number 4, and this LED extinguished. If I plug it back in, it gets illuminated. Now, the numbers are reversed on the upper portion, so core number 1 is actually physically connected to channel 4 on the harness that goes to the UR. Channel 2 is actually going to channel 3 in the universal relay. Core 3 is going to channel 2 on the UR, and core number 4 is connected to channel 1 in the UR. So here's our brick with all the cables connected on it. We have cable A here, which is our communications and power supply for the brick. Cable B is our contact outputs. Cable C is our contact inputs, and cable D is our CTVT connections. All of these are terminated back into this RTT device that we're going to be using, and This is going to be our CT-VT connection. This is our digital inputs and our RTD connection. So we'll go into the remote resources and we'll configure the communication between the brick and the UR. We'll set up the remote resources for a CT ratio of 1000 to 5. The VT secondary with 35 volts. The VT ratio will be 6571.42. Alright, so what we're going to do is under settings, we'll come into remote resources. We'll open up the field units AC bank resources. And I'm going to minimize these other screens so we can see the whole thing at the same time. Let's give this all a name. So these are the 8 individual bricks that the relay can communicate to. We're using all 4 channels on a single brick, so we'll just go in and rename the individual channels differently. So I'll just call this, we'll call it line A. Core 1. Next one, line A. Core 2. So forth, so on, 3 and 4 all the way down. We'll need to enable the function. We have to indicate what type of brick we're dealing with. So these would be, the brick that we're using is a CV5. The serial number we'll leave alone right now. Now, one of the things that we have to look into here is which core is connected to which connection on the back. In our previous discussion, we had indicated that core 1 was going to be connected into 4B. That core number 2, you can see we have the choice of 4 cores. Core number 2 is connected into 3B. Core number 3 was connected into 2B, and core 4 was connected into 1B. Now let's save that. Alright, right now we're getting an equipment mismatch. Next step we have to do is we have to come in here and select the auto populate, and you can see it's already populated here with the serial number of the device. You just click on change. Let's go all the way through it. We'll need to go back and change it again. Now that we've got the OK, that indicates that everything is communicating. On the front of the brick, we have all the lights have turned green. The next thing we'll look at is setting up the banks. The banks here are labeled U1, C1 through 1 to 3, U1, C5 to 7. So these are AC inputs, AC 1 to 3, AC inputs 5 to 7. What these are indicating is 1, it indicates that it's phase A, 2 is phase B, 3 is phase C. On 5 to 7, it's the same arrangement as it is on the DSP card. Number 5 in this case would be phase VA, 6 would be VB, 7 would be VC. So that's the breakdown, that's the correlation between the two. So what we're going to do is we're going to set up the first bank to be this. So unit 1, we're going to look at IA, IB, IC will be assigned to bank 1. I'm going to look at the second core and I'm going to do the same thing with it. IA, IB, IC will be coming into the second core. And bank 2, I'm going to put in connections AC 5 to 7, which is VA, VB, and VC, unit 1, and the same thing for unit 2. Now, the next thing, we have to place the CT ratio in here. We had indicated that the CT primary was going to be 1000 amps. The CT secondary has to be 5 amps because it's a CV5. Under bank 2, we're going to put in the specifications for the voltage, which in this case was going to be a voltage ratio of 6571.42 and a VT secondary of 35 volts. We'll leave it as a Y. And as we had before with the DSP cards, same thing, we have to give the source a name. So I'll call this line A, and then we populate it in the same manner, except instead of going F1, M1, we're using these as reference points. So I'm going to use bank 1 for the current portion, and I'm going to use bank 2 for the voltage source. I'll go ahead and save this. Okay, the next thing we'll take a look at is the current inputs. Let me bring my menu back on board. Field contact inputs. These are the contact inputs for our status. So one of the things that we can put in here is things such as, just get a name like this, 52A breaker 1. 52A breaker 2. I'll just put another one so we have that in there. So we'll populate the first 3. So these are the labels. Over here we indicate which module or which brick we're going to be using as a reference. We have the choice of the 4. These are the naming conventions that we gave them. And of the 18 input contact inputs, which one are we going to be assigning to this ID? So in this case, I'll put in number 1. Same thing again, I'll put in contact number 2. I'll put in on this one on number 3. And I'm going to do something different here. I will do a backup for these breakers. I'll call it 52A breaker 1 BU, and let me just copy that all the way down. We'll do the first 3. So I'm just going to relabel this as number 2, and this one will be number 3. But I'm going to assign this to the second core. So the second core is coming in through field unit U2. It'll come in from contact input 1. And then this one will be input number 3. So the idea here is this. This is going to, core 1 will be the main. And if we close the contacts, then these will become active. And it'll also be coming in through here as well. If we have a break in the connection on this part, then the signal coming in from the brick will still be coming in through a second source. So that's the idea behind it. A contact outputs. The other thing we're going to do is we'll look at the what we call field contact outputs. And these are the same kind of indication. So let's force this with something. We'll call this manual trip, and let's call this manual close just to give it a name. And the signals that we'll use here will be the field contact 1, which was our 52A. So there's the first one. Then we do a copy paste, and I'll just make it the second one just so that we can see the operation of it. Okay, so now we've configured our sources, we've configured our contact inputs and our contact outputs. So now we'll go back. Now we'll go out and verify the operation. Now let's go ahead and verify the operation of the brick. On our actual values, let's come down to the metering portion, go down to the source, phase current, phase voltage. Let's inject some voltage and some current. Alright, there's no values being presented. The reason for this is we need to reboot the relay after we've changed settings in the brick. So let's go ahead and reboot this. This is located under maintenance. Now that we rebooted our relay, you can see we have metered values being displayed as we adjust our current and our voltage values. We are seeing some fluctuations. Let's confirm our inputs and outputs as well. So in that, we'll come down to the remote resources, and we can have another look at the way we're set up here. We can verify that the communications are operational still. We can see our metered values, or sorry, we can see our configurations for our resources. Take a look at the contact inputs. If I close switch 1 on the box, then we can see that the status has changed. If I close switch 2 and close switch 3. Now, why is it showing up in two places? The reason it's showing up in two places is because we're monitoring the same brick contact input changes from two different cores. This one is from core 1. This one is coming in from core 2. If I open up the connection, so now if I go ahead and open up one of the connections, if I open up core 1 and remove and break that connection, we'll see an error appear on the relay. There's an alarm. We've lost link 1. In the software, you can see that we've lost core 1 connection. If I remove core 2, then I'll lose the second indication as well. So I'm just removing the second connector, second fiber, and now you can see that it drops out as well. If I return the connections, then they both become active again. The other thing we can confirm as well is the contact outputs. So we can take a look at the field contacts outputs, and this is based on the closure of these two contacts. Contact input 1, contact input 2. This field contact input 1, field contact input 2. As I close them, And we'll see the output relay switch on as well. I switch it off. This switches off. I turn on number 2, and you'll see the activity turning on as well. The brick has the same functionality as the DSP cards, so we can actually go into the protection summary and repeat some of the tests. So if we come back in here, and let's say we want to do the instantaneous overcurrent. We can select it, we can enable it. Let's reduce our inputs just because we're limited on the equipment. We'll reduce this to, say, 0.3 per unit. I'll set this up as latched and enabled. So that now we come back to the screen, the IOC is enabled, and let's just do a quick verification. I'll go to the front panel so we can see what's going on. And again, we'll increase the current. And we see the same type of configuration. Okay, it operates the same way as the DSP card. All right, so this concludes our testing of the brick. Thank you so much for viewing.